Before we hop into path diagrams, we need to understand the variance and covariance matrix. The variance covariance matrix is more than a mathematical artifact. It's a powerful and multifaceted tool that plays a crucial role in statistics and data analysis. In a variance covariance matrix, recall that there's diagonals, and the diagonals are the variances of each item. And in simpler terms, they tell us how much a particular variable deviates from its mean. And they're important because understanding the variance of a variable helps us grasp its stability or volatility. In clinical psychology, for example, a high variance in a symptom may indicate significant fluctuations in a patient's condition, which could inform treatment strategies. Then we got to look at our off diagonals. The off diagonals in the matrix represent the covariances between pairs of variables. This helps us comprehend how two different variables change together. By studying the covariances, we can identify relationships between different variables. For instance, identifying a positive covariance between two psychological symptoms may lead to a better understanding of their underlying causes and thus more targeted therapeutic interventions. Now let's think about symmetry. It refers to the mirrored nature of the matrix, meaning that the correlation between two items is consistent regardless of their order. And this property not only simplifies our understanding of the relationships between variables, but it also ensures mathematical consistency within the matrix. It's a fundamental aspect that validates the relationships between variables and makes the interpretation more straightforward. For correlation magnitude, this helps us understand how strong relationships are between variables in most analyses. A correlation above 0.30 suggests a medium or meaningful relationship between variables. By discerning these correlations, researchers can begin to make predictions or understand underlying patterns, which might lead to more effective interventions or treatments in a clinical setting. Let's briefly review factor analysis again. Remember that factor analysis is a technique that allows us to make sense of complex, multifaceted data. It's a statistical method used to reduce a large number of variables into fewer underlying factors. These factors represent the underlying constructs that explain the observed correlations among variables. It's important because by simplifying complex data into manageable factors, we can make more sense of it, leading to clearer insights and more robust conclusions. The factor analysis model helps us delve into the unseen variables that are affecting our observations. Now, regarding factor analysis versus linear regression, understanding the differences between factor analysis and linear regression is essential for appropriate model selection. For the differences, factor analysis works with multiple outcomes per subject, not just one. The predictor in factor analysis is latent or unseen, unlike the observed predictors in linear regression. The importance of this is that by recognizing these differences, you're going to be able to select the right tool for your research. And this ensures that the chosen method aligns with the research questions and the data structure. Regarding equations and model implied covariance matrices, these equations articulate how the underlying factors, the intercepts, the loadings, and the residuals work together in the factor analysis model. Why are they important? These equations form the mathematical backbone of our analysis, providing a structured framework to describe the observations. They translate the conceptual ideas into a form that can be computed, tested, and interpreted, thereby enabling researchers to quantify abstract constructs such as anxiety or depression. As a summary, the variance covariance matrix and the factor analysis model are vital instruments in this toolkit of psychologists, researchers, and data analysts. They enable a deeper understanding of complex data, and they facilitate the uncovering of hidden patterns, and they also guide both theoretical exploration and practical application. From identifying relationships between variables to simplifying multifaceted data, these tools are at the heart of modern psychological research and practice, and they offer insights that drive progress in the field. Understanding them fully is not only an academic exercise, but a practical necessity for anyone engaged in the complex task of unraveling the human mind and behavior. And now we can start talking about path diagrams and all these concepts from these two slides. They're a visual way to represent complex equations. In the context of structural equation modeling and factor analysis, path diagrams are this indispensable tool for both seasoned researchers and newbies. They offer a simplified visual representation of the complex mathematical equations that underlie these statistical models. Let's start off with the symbols. The symbols used in path diagrams, as seen here, are not merely artistic flair. They're an integral part of communicating the structure of the model. And let's do a deeper exploration. The circles represent latent variables, which are underlying unobservable constructs that the model aims to measure. Then there's the squares. These symbolize observed variables or indicators. They are the measurable data that are analyzed to understand the underlying latent constructs. Then the triangles, they're often used to depict means or intercepts. These add another layer of complexity and information to the model. The arrows, these can be both one-way or bidirectional. One-way arrows represent regression paths or causal relationships, while the bidirectional two-way arrows signify variances or covariances. Why do we bother with these symbols? Well, they're not just a convenient shorthand, but a vital part of understanding and communicating the model. They give us accessibility because by translating equations into visual terms, path diagrams make complex models more approachable, particularly for those new to the field. They also give us clarity because they clarify relationships between variables, making it easier to see how each part of the model interacts with the others. They also help us with communication because they facilitate discussion and collaboration among researchers by providing a shared visual language. Regarding parameters and identification, in the context of a model, parameters are the numerical quantities that define its characteristics. Let's delve into the key ones. The loadings, which are represented by lambda. These are correlations with the factor, signifying how strongly an observed variable is related to the latent variable. They can also be interpreted as the regression weights of the latent variable on the observed ones. The factor variance, denoted by psi, this is the variance of the unseen latent factor. It reflects how much the latent variable varies within the population. The residual variances, represented by theta sub epsilon, these represent what's left unexplained after the latent factor's influence has been accounted for. Essentially, it's the noise or air in the observed variables. Let's look at this second figure right here. The diagram on the left depicts the regression of a factor on an item, essentially a measurement model. And the diagram here on the right depicts the variance of the factor because it's a two-way arrow pointing to a latent variable. If we look at this path diagram here, all measurement model parameters are color-coded in green, and all model implied covariance parameters are coded in blue. As a general rule, only paths, which would be represented by lambda and tau, and the bidirectional arrows, represented by psi, are estimated, not the circles or the squares, meaning y, eta, or epsilon. Then the only green paths are lambda and tau, and among the blue, again, lambda is estimated, as well as theta and psi. However, the lambda is the same across measurement and covariance models, so we don't need to estimate them twice. Traditionally, the tau is not estimated, which means that all the parameters we need can come directly from the covariance model. In the model implied covariance, we assume that the residuals are independent, which means that, for example, theta sub 2,1, the covariance between the second and first residual is set to 0. As such, the only covariance terms to be estimated are psi sub 1,1, which is the variance of the factor, and theta sub 1,1, theta sub 2,2, and theta sub 3,3, which are the variances of the residuals, assuming heteroscedastic variances. As an exercise, let's see if we can map the path diagram here to the following regression equations here. The variable y sub 1 is equal to tau sub 1 added to the product of lambda sub 1 and eta sub 1, and then further added to epsilon sub 1. The variable y sub 2 is equal to tau sub 2 added to the product of lambda sub 2 and eta sub 1, and then further added to epsilon sub 2. And the variable y sub 3 is equal to tau sub 3 added to the product of lambda sub 3 and eta sub 1 plus plus epsilon sub 3. These equations are going to represent relationships where y sub 1, y sub 2, and y sub 3 are the observed variables or our outcomes. Tau 1, tau sub 2, and tau sub 3 are the intercepts or the means for each observed variable. Lambda sub 1, lambda sub 2, and lambda sub 3 are coefficients representing the relationships between the latent variable, eta sub 1, and the observed variable. Now remember, eta sub 1 is a latent variable or the underlying factor. And lastly, epsilon sub 1, epsilon sub 2, and epsilon sub 3 capture the unexplained variation in the observed variables. Now, let's look at the last equation on the bottom right. This says that the sum of theta is equal to the product of three matrices and the addition of another matrix. The first matrix is a column vector that consists of three elements, lambda sub 1, lambda sub 2, and lambda sub 3. The second matrix is just a single element. It's the column vector containing the element psi sub 1, 1. This third matrix is just a row vector that consists of three elements, lambda sub 1, lambda sub 2, and lambda sub 3. And lastly, the fourth matrix, which is being added to the product of the previous matrices here, is a 3 by 3 matrix. The elements on the diagonal, as we talked about before, are theta sub 1, 1, theta sub 2, 2, and theta sub 3, 3. Here are the off-diagonal elements, the zeros. The entire expression represents a mathematical relationship, which might be part of a more complex system or model, possibly in the context of statistics or some other scientific field. The path diagram and the equations quickly inform us of the parameters coming either from the measurement model or the model implied covariance. And knowing how to count parameters is a very essential skill to have in confirmatory factor analysis. Traditionally, we disregard the parameters in the measurement model, i.e. tau, and here we're going to focus on the parameters from the covariance model. Let's see if we can count the number of parameters from the equations or the path diagram above. As an analyst, knowing how to count the parameters is crucial in understanding this CFA concept called identification, which is going to be the subject of the next video. So the answer here is that there are three loadings. We have lambda sub 1, lambda sub 2, and lambda sub 3. We have one factor variance, psi sub 1, 1, and three residual variances, theta sub 1, theta sub 2, and theta sub 3. However, we only have 6 known values from the observed covariance matrix. Understanding these parameters is central to interpreting and utilizing the model. They provide insight into the underlying structures and relationships in the data. They help us with decision making. Parameters guide choices in model refinement and help assess whether the model fits the data well. They give us predictive power. Understanding parameters like loadings can help in predicting outcomes and guiding interventions in practical applications. So to conclude, path diagrams are far more than mere illustrations. They are a crucial part of our toolkit for understanding, interpreting, and communicating complex statistical models. By visually representing relationships, they make intricate structures comprehensible and accessible. The parameters within these models, such as the loadings, the factor variance, and residual variances, provide the numerical backbone to these visual representations. Their understanding is essential for anyone looking to deeply engage with the data and extract meaningful insights. As future clinicians, these tools are not abstract concepts, but vital instruments that help untangle the complex interplay of mental processes and behaviors. They help researchers and clinicians alike to build more robust theories, design better interventions, and ultimately improve mental health care and outcomes. In the next video, we're going to take a deeper dive into these diagrams and model identification.